Okay, let's get started. Let's talk a little bit about the assignments before we jump back to lecture. Everyone managed to submit assignments 2 and 3. We're clear on neurons and synapses, activation functions. We're all good? Okay, so I won't talk about assignment 2 and 3 then. I'll talk a little bit about assignment 4. Before I do, as I mentioned at the beginning of this class, when you finished all 10 assignments, you're going to have 2 executables running in parallel. You're going to have your Python executable, and it's going to be talking continuously to your physics engine. So assignments 1, 2, and 3, you've been building up your Python executable, which for the moment creates neural networks and evolves them to do something, right? So we're going to set your Python code aside now, and assignments 4 through 10, you're going to be building up, or assignments 4 through 8, you're going to be building up your C code, your physics engine, and then in assignments 9 and 10, we're going to put these 2 pieces back together again and have them talk to one another. And what you're going to have these 2 pieces of code doing by assignment 10 is your Python code, instead of creating neural networks and evolving them internally in the Python code, you're going to export a neural network into the physics engine, and that neural network is going to animate a robot. And you're going to then send back from the physics engine a single number, which is the fitness for how well the robot did. With your neural networks at the moment, you're deriving a single number, a fitness value, which is how well your neural network matches the checkerboard pattern or what have you, right? So neural network from Python to C, evaluate the robot, send the fitness value back, create a new neural network, send that to the physics engine, and around we go. Make sense? Okay. For a lot of students, assignment 4 takes the most amount of time. Not because it's intellectually challenging, but because there's a lot of installation headaches. So definitely get started on assignment 4 as early as possible. Has anyone run ahead and tried to install the Bullet physics engine yet? Okay. Any success, Lily? Okay. All right. So the challenge in assignment 4 is obviously you all have different computers. We've got Macs and Linux. You have different C compilers. We can potentially have different versions of the Bullet physics engine, so please don't assume that the TA or I is going to know how to install Bullet for your particular platform and your particular compiler. We've done our best to try and cover all combinations and permutations. So if you get stuck, obviously consult the web, see what you can find out. If you're still stuck, I'll show you in a moment, there is some resources in the Reddit part of the course. Students before you might have had the same platform and compiler, and they might have put up instructions about how to install Bullet for your combination. If you're still stuck, come and see Owen or myself, and we'll see what we can do. Sound good? Okay. So let's jump to the subreddit for the course for a moment. So basically in assignment, as I just mentioned, assignment 4 here, you're going to be installing and configuring the Bullet physics library. There's a lot of different physics engines out there. They all have their pros and cons. We're going to be working with Bullet in this one, and I want you to focus on installing version 2.82. I see that just recently they've released Bullet 3 or 2.83. I don't know if it has everything in there that we need. I do know that everything you need is in 2.82. You can get the download at code.google.com. Let's all at least make sure we're all working with exactly the same version of Bullet. Okay, so download Bullet 2.82, get it installed, and when you do, you will find after installation that it comes with a whole bunch of demonstrations. One of them is the ragdoll demonstration, and I'll bring up a video so you can see what this looks like. So this is what you should get right out of the box after you've installed the physics engine. So here's your little ragdolls. You can see the ragdolls are made up of a whole bunch of objects that are attached together with passive joints. We'll talk about what that means today when we talk about the internals of a physics engine. As you can see, you can grab different objects with a mouse and throw your ragdolls around. So that's what you're going to get out of the box with this demo. Once you have this demo, as I mentioned in assignments 4, 5, 6, 7, 8, and 9, we're going to be ripping out the ragdoll part and incrementally adding in all the parts of your robot. And then in assignment 10, you're going to be actually evolving the robot. So rather than creating an empty physics engine and going from there, you're taking a demo that already works. You're going to be taking the ragdoll out and putting your robot in. Okay. So when you do, for this assignment, you'll be submitting 4 screenshots. First one is just showing us that you've correctly installed and you're able to run the demo out of the box. Then you're going to be altering your ragdolls into bobbleheads. So you're going to go into the code for the first time of the physics engine and make your first modification to, in this case, the ragdoll that exists in this virtual environment by just increasing the size of the ragdoll's heads, just for fun. So you can demonstrate to us, you know how to go into the code and modify parts of, in this case, the ragdoll. As you can see here, the demo comes with 2 ragdolls. You're going to go back into the code and figure out where a ragdoll is created and take that part of your code out. So you only have 1 ragdoll created. Delete the second ragdoll. So by the end of assignment 4, now you have a clean slate. So now when you start up your executable at the end of assignment 4, it creates the virtual environment, but there's nothing in that environment. And in assignment 5, you're going to start adding in all the bits and pieces of your robot. Make sense? Okay. Start early on assignment 4. Some of you, it might take a few minutes to get things installed. Some of you, it might take a little longer. Okay, good luck. Okay, so just to reorient you, again, we're working our way through the tools of the trade. We're going to finish lecture 5 today, our discussion about evolutionary algorithms. In lecture 5, we started with the simplest possible evolutionary algorithm you could imagine. It's not really an evolutionary algorithm, because you don't even have a population of individuals, you just have a single individual, which is the hill climber, right? We're going to talk about versions of that in the rest of lecture 5 today, and then, good timing for us, we'll start in and probably finish lecture 6 today on physical simulation. As you can see, the reading for today, not surprisingly, is parts of the Bullet user manual. One of the drawbacks of Bullet, unfortunately, is the documentation is not great, but it is there. You should be able to find most of what you need somewhere in the user manual. If you have a specific question about Bullet that has to do with the assignments, you might also want to post a question in the subreddit. Former students who are still on the subreddit are pretty good about getting back to you, and Owen and I will also try and answer your questions if they show up on the subreddit. Okay, so we're going to familiarize ourselves a little bit with physical simulation today. But again, before we do, let's finish our discussion about evolutionary algorithms. So again, all evolutionary algorithms share one thing in common, which is they all borrow the basic underlying algorithm of evolution, which is descent with modification. You have a population of things. Those things are genetically diverse somehow. The genotype dictates the phenotype, which is the body of the animal or the body of the robot, and the behavior of the animal and the behavior of the robot. Those that do what we want them to do, in the case of evolutionary robotics, we keep. Those robots that don't do a very good job, we throw them away. And the robots that survived, we take them and make randomly modified copies of them, evaluate the new robots, and rinse and repeat, right? That basic algorithm is there in all evolutionary algorithms. Different evolutionary algorithms add different bells and whistles to that. One of the things that we introduced last time to guide our growing intuition about evolutionary algorithms is the idea of a fitness landscape. So in a fitness landscape, you can imagine every individual, or in our case, every robot, as a point in this high-dimensional space. And as it moves horizontally in the space, it's moving because of a mutation. So any given point corresponds to any given genotype, and the height of that point is the fitness of the phenotype associated with that genotype. Right? That's the fitness landscape. We looked at the hill climber last time. The hill climber, as you now know, is very, very simple to implement, a few lines of code, but it's relatively weak in the sense that it will climb whatever hill it starts on in the fitness landscape, but will very quickly get stuck if that hill is not the highest hill in the fitness landscape. So these local optima are these local hills, right? They're pretty good solutions, but they're not on the path to the best solution, which is out there. Okay, so we can try and enrich the hill climber by creating a parallel hill climber where now we have not an individual parent, but a whole bunch of parents, and they're producing children. So in essence, we have a whole bunch of hill climbers distributed through this whole space of all possible genomes, and they're all climbing their local hills, which is better, but still not great, because we have to hope that those original parents landed on, or at least one of those original parents landed on the slope of the global optimum, right? The tallest mountain in the fitness landscape. So next algorithm up from there is the genetic algorithm, where again we have a population of genomes, but now sometimes we're going to mutate solutions when we copy a parent, and in other cases we're going to take two parents, pull them in half, and combine two parts from two different parents, which is adding in sexual recombination. And hopefully, if we do this right, in some cases, when we do this recombination, we just happen to bring together the best of both worlds. A good part of parent 1 with another good part of parent 2. And if we do that, we might actually bring the child to a very different part of the fitness landscape, which happens to lie on the slope of the tallest mountain. Okay. We ended last time by introducing the evolution strategy, which takes a little bit of the randomness out of this process, right? The other thing that all evolutionary algorithms share in common is it's random trial and error. But if we want to mutate or sexually recombine two individuals, how do we do it? We don't necessarily have to do it completely randomly. So in the evolution strategy that we looked at last time, each gene in the genotype or in the genome has an associated number with it, which is the magnitude of mutation that's good for that gene. And I walked you through last time using the fitness landscape to build up an intuition for how this works. So if you're in a relatively smooth fitness landscape, which means that at any given point you can make steps and you're likely to increase fitness. But in a rugged fitness landscape, like you see it over here, any given genome, if you make too much of a change, you're likely to fall off your current hill or mountain completely. So as evolution proceeds, it makes sense to take smaller and smaller steps. These numbers, which dictate how much or how small the mutation is, are themselves under evolutionary control, right? So evolution can figure out this gene should still be mutated by a large amount. That seems to work pretty well. But this gene over here, whenever I make a change to it, things tend to get worse. But oh, I just made a small change to this gene and things got better. So maybe I should shrink this number a little bit. So each number has its own mutation magnitude associated with it. That's the evolution strategy. Okay. A lot of other evolutionary algorithms out there that try and take a little bit of the randomness out of evolutionary algorithms. Okay, let's look at another evolutionary algorithm. This one is actually called genetic programming rather than a genetic algorithm. And the reason this is called genetic programming is originally it was used to evolve not strings of numbers or vectors, but it was used to evolve trees, and those trees represented computer programs. So one of the interesting applications of genetic programming is you can use it to evolve code rather than writing code by hand. We're not going to talk about that application of genetic programming today. We're going to talk about using genetic programming for another problem, which is known as symbolic regression, which I'll introduce you to in a moment. As you can see in the cartoon here, however, we have two parent genotypes here. So in genetic programming, the genotype is represented as a tree, rather than as a string of numbers. That's the main distinguishing feature of genetic programming compared to all other evolutionary algorithms. Now, what those trees represent depends on the problem you're trying to solve. If we want to use genetic programming to evolve code, then those trees represent computer programs. If we want to perform symbolic regression, which I'm going to walk you through now, the trees represent equations. Okay, so if you haven't seen trees being used to represent equations before, it's not that difficult. All of the internal nodes to the tree, as you can see here, are operators. They can be algebraic operators, trigonometric operators, doesn't matter. Whatever you want to throw in there for your equations to play around with. The terminal nodes down here in the tree represent floating point numbers or variables. So on the right here, what I've shown you, you can think of this as a bag, and that bag is made up of a whole bunch of operators that we think might be appropriate to our problem, and a whole bunch of operands, some floating point numbers, and some variables. When we start by initializing our population to run genetic programming, we're going to create a population of trees, or a forest if you like. So if we have a population of 100, we have 100 trees in there, and we construct those trees at random. So we start with tree 1, or P1 if you like. It's an empty tree. We reach into our bag of operators and operands, reach around at random, and pull out, in this case, multiplication. Multiplication requires 2 arguments, so we root multiplication at the root, create 2 empty subtrees, come down to this first stub of a subtree, reach into the bag again, grab an operator or operand at random. In this case we grabbed plus, plug a plus in there, come down here, reach into the bag again, we grab 0.8, we go over here, grab in the bag again, we grab x, and so on and so forth. So P1 and P2 here, you can think of these as just 2 random trees that were created by reaching into the bag, and around we go. Okay, and we do that to create 100 trees. Now it's a pretty simple procedure that I just described to you, but there's a bit of a problem with doing things that way. What is it? It could go on forever, right? So you're not always guaranteed that you're going to create a finite tree. So maybe we put a maximum cap on the size or the depth of the trees. So if you're still grabbing operators when you're at 17 levels deep in the tree, you have to grab an operand. So we have some way of forcing the tree to be finite. Okay. So let's say that we do this, and we're not going to say what these equations are trying to do. I haven't said anything about the fitness function yet, and I haven't said anything about the phenotype, what these trees do. So at the moment, we're just talking about the genotype, and remember the genotype is the data structure that stores the blueprint of the phenotype. So we've got our genotype, which in genetic programming are always trees. And we can mutate and cross these trees like before. So for you here, I've just taken this equation here and written it out in a more familiar form. So this tree encodes the function multiply this term by this term. And this term is 0.8 plus x times 1.4. Pretty straightforward. Okay. How would we introduce sex to genetic programming? We have these 2 parents. How are we going to recombine genetic material from these 2 parents to create 2 children, trees which are similar but not identical to the parents?
Maybe either swap leaves or take one of the leaves that has an operand and make it the new root.
Okay, we could do that. We could grab an operand and make it the new root. What else could we do? There's a bit of a hint for you here based on how I've drawn this slide.
Subtree, just switch them.
Switch the subtrees, right? One of the nice things about genetic programming is it makes crossover very easy. So we're going to recombine genetic material from these 2 parents here, and let's imagine that I pick a node at random in this parent, which is the red node here. And then I go over here and I also pick a node at random. In this case, I happen to pick this subtree here. Doesn't have to be the subtree that's in the same position in both trees. I could have picked this node, doesn't matter. I picked these two subtrees. I pull them off the parents and just swap them. I take the subtree from this one, put it here, take the subtree off here, and put it there. And now if I plug them back on, we now have C1 and C2, two children, and I've now written out the equations again, and if you compare these equations to these equations, they're similar to, but not identical to, the parents. Okay. That's crossover for genetic programming. How would we do mutation? So imagine we have just one of the parent trees up here, and we want to introduce a little bit of a random change to that single tree. How would we do it? Tyler?
If you pick a terminal node, then replace it with a random terminal node, or if you pick one of the operators and replace it with another operator.
Okay, so we could grab a terminal node at random and replace it with a new random terminal from our bag of possible terminals. We could grab an internal node and replace it with an operator from the bag. Do we have to replace a terminal with another terminal and an operator with an operator? We could force it to do that. Don't necessarily need to, right? We could pull off this terminal node, reach into the bag at random, and it doesn't matter whether we grab an operator or an operand. Let's say we grab the division, we plug division in here, but division needs two arguments, so we reach into the bag again, and this one node subtree gets replaced with a new subtree that's a little bit bigger. Are there pros and cons to these two approaches? So Tyler proposed a kind of restrictive mutation operator where we replace terminals with terminals and operators with operators. I gave you a different mutation operator that's a little bit less restrictive. Does it matter?
You can't replace an operator with a terminal node, can you?
You could, as long as you assume that when you pull off the operator, you also delete everything under the operator. That's a good point. Okay, when we talk about replacing a subtree, we usually mean we're pulling off the whole subtree and throwing it away. What about, let's assume we're going to do mutation, and I pick a node at random for where mutation is going to occur, and I pick this node for mutation. What's going to happen? It's going to change the whole tree, right? So if I grab the root node, throw away the entire tree, I'm in essence creating a whole new tree from scratch. Do you think that new tree is going to do well? I haven't told you what the fitness function is yet or the phenotype, but intuitively speaking, given your intuition about evolutionary algorithms so far, what about that mutation compared to another one where I grab this node, pull it off, and replace it with another terminal?
It depends on the value of what you've already done. So if you created something valuable and spent a lot of time, obviously, that would be a waste.
Right.
If you found it was really bad,
Then it doesn't matter.
maybe you
Exactly.
throw it all out.
That's right. It depends on the fitness of the original tree. If we've been evolving things for a while, and this tree has a relatively high fitness, it's already doing part of what we want that tree to do, and we delete it and replace it with something random, that new thing is quite likely to be much less fit than something else. If I pull out the guts of your laptop and fill it with random circuitry, what's the chance that that laptop's going to work, right? Not very much. If I opened up your laptop and went in there with some tweezers, this probably still also wouldn't work, but imagine that I could make a very, very small change by taking one node way down in the bottom of the tree and replacing it with a new node that's kind of similar. Maybe I delete 0.8 and replace it with 0.801, right? very minor change, more likely that there's a much higher chance that that random change might actually improve things a little bit. There's a whole literature, thousands of papers have been published on these kinds of topics. So I've just described two variation operators to you, one which mutates trees and one which sexually recombines material from two trees. There's thousands of operators that have been described in the literature. They all have their pros and cons. It's an interesting thing to think about, how we would actually vary trees in a way that increases the chances that those new trees might do a little bit better than their parent trees. Okay, so we've only been talking about genotype so far. So let's talk a little bit now about phenotype. Let's set genetic programming aside for a moment, and now let's think about data. Let's imagine someone comes to you and says, I've got this data table here. There's a certain number, there's a variable here, x, that I've measured, and I've measured it several times. And whenever I measured it, it had this value. When I measured it again, it had this value. I measured it again, it had this value. And for each of those values, there was some other value in the system that I'm interested in that I measured. We'll call that y, or the dependent variable. And it had these values. And if I plot x versus y from this table, I get this scatter plot. And I'd like to know if there's a relationship between x and y. So cast your mind way back to high school. Is there a relationship here, given these little cartoon points that I'm showing you? What is it? I've got y equals question mark here. I'd like to write down an equation that captures the relationship between x and y. Sorry?
Y equals x squared.
Y equals x squared. How does that sound to people?
Plus 3.
Minus
Minus 3. Yeah.
All right,
Minus
recall your high school. We're getting close. X squared was close, but not quite.
X minus 3 squared.
Thank you. Okay, there you go. All right, so let's do what we just did. Let's make some guesses for equations and see how well they do. There's a little typo on the slide here. This should not be y prime. This should be y equals x. Let's start with that, not even x squared. I'm going to try y equals x. And if I do that, that's going to lead to a whole bunch of points that lie along this line. I haven't shown you the actual points. I've just drawn the line. How good is y equals x? Well, there's a way we can automatically measure that. For every value of x, let's look at the actual y value and the y value that's produced by our candidate equation. And the thin line here represents the amount of error. So this particular equation is doing a very bad job of predicting for this value of x what the value for y should be. The actual value of y is this. Our model is saying the value of y is this. Not very good. This one, okay. This one pretty bad. This one terrible. This one not so bad. Right? So not very good at all, right? So let's take x, y equals x, and throw it away. And now let's try y equals x minus 3 squared, which gives us that curve here. Now it's not perfect. There's still some that are off, but there's many fewer of these lines than there are over here. There's the equation in the top right that we could use to actually compute the total amount of error. So in this equation here, xi and x prime I, these are just each of the positions. This is the ith value of x here, and y and y prime. yi is the actual y value from our table, and y prime is the value predicted by the model. So far, so good? Okay, so let's imagine now we had a whole population of these equations, and for each equation, we generated the y primes over here and summed up all of the error produced by that particular equation. Assign that to the equation, go to the next equation in the population, compute the total amount of error, and continue to compute the errors for all of the equations in our population. We're now going to, as you can imagine, evolve these equations. What do we do next now that we've computed the error for all of these random equations? What have we done in all the evolutionary algorithms you've seen so far?
Throw away the really bad ones.
Throw away the really bad ones. And what are the bad ones in this particular example?
High error.
High error, right? So throw away the ones that have error that's higher than the average error in the population. Let's just make something up. So that'll throw away about half of the equations. The ones that remain, as long as they're encoded in a tree, we create mutants and crossed versions of those trees to fill in the slots of the ones we just deleted. So we have a whole bunch of new equations that are similar to but not quite the same as the ones before. Compute the errors of those new equations. So now again we have a full population of equations. Compute the average error for all the equations in the population. Throw away those that have error higher than the average error. Repeat, repeat, repeat. And if this is working, you should eventually find that your population is filled with equations that are some algebraic equivalent of x minus 3 squared. Okay, so why is that called symbolic regression? Well, some of you might have seen linear regression before. And in linear regression, as the name implies, you assume that your points can be fit with a line, and you optimize the parameters to try and move this line so that it's as close to as many points as possible. That's called linear regression. Some of you may have heard of nonlinear regression, which is now you don't need to assume a straight line. You can assume a squiggly line, and some of the parameters that describe that squiggly line are going to move that squiggly line a little bit, but I won't get into the details. It's still kind of restricted in what the shape of that line can look like. Symbolic regression says, why assume we have a straight or a squiggly line or a polynomial line altogether? Let's just trash that and start with a random bag of operators and operands and allow evolution to put together arbitrary equations until it comes up with one that fits all the points as best as possible. Let's allow our machine learning algorithm to manipulate the symbols rather than the parameters that describe an equation. That's symbolic regression. Okay. Why does our x minus 3 squared not perfectly fit all of the points here? What did I add to this little cartoon here of scatter points? So clearly these points are not perfectly described by x minus 3 squared.
Plus 0.6.
Could be, so we could try and move everything up and we might get closer to these, but we'll also move further away from these. So what I've done here is to add a little bit of noise. Let's imagine that the system that produced these points, the underlying system actually does obey this equation, x minus 3 squared. But every time we measure y, there's a little bit of noise. So we get an actual y value that's a little bit above or a little bit below. We're going to come back to the issue of noise many times in this class. If we have a robot and it's sensing the world around it, it's never sensing the world perfectly. Its sensors are not perfect. Your sensors aren't perfect either. A big part of what your brain does is to erase the noise so that you don't see it. Okay, so in this cartoon here, actually, if we let genetic programming continue, it would blow past x minus 3 squared, and it would go onward because there's probably a more complicated equation out there that will give us an even more squiggly line that will touch more of the points. Depending on how far apart those points are, that equation might start to get pretty hairy indeed. And that's probably not what we want it to do. And that's a problem in machine learning that we've already talked about. What was that problem? Overfitting, right? So if you remember back to our discussion about artificial neural networks, given a large enough neural network, it will memorize all of the things it's seen rather than look for the underlying pattern that produced all those examples, right? It will memorize last year's midterms in the hope that this midterm is the same as last year. In a similar way, this completely different machine learning algorithm, genetic programming, if you allow these trees to get big enough, will eventually give you a horrendous curve that will end up touching all the points. but intuitively we would probably feel that whatever that massive equation is, it hasn't captured the underlying structure of this system. Okay. Just to give you a feel for the ubiquity of this problem of overfitting. Okay, so symbolic regression, who cares? It turns out this has immense practical value. Here's an example from a research project I worked on a few years ago, a problem very close to home. If you know Lake Champlain at all, you know every summer and some summers in certain bays in the lake, there are these toxic algal blooms. Not a good thing. You don't want to go swimming in there. Nobody knows why. Everybody knows, or a lot of people know, certain things that influence these toxal blooms. So phosphorus that flows out of farmland and into the lake, fertilizer, that's part of the problem, but it's not the entire problem. So let's see if we can figure out a way to do this. So let's do this by creating a data set where every row in our data set here corresponds to a different place in the lake and a particular day, so a particular place and time. And at that place and at that time, we're going to measure a whole bunch of variables. So now we don't have X and Y, we have N, P, W, B, and R, and we could have more depending on what lake scientists think is important. And finally, the most important one here, our dependent variable, the total amount of toxic algae. Some parts of the lake, relatively little at that point in time, other parts of the lake at another point in time, quite a bit of that algae. All right, go. What do we get? We want an equation. We're going to use genetic programming to try and figure out the right-hand side of this equation. What actually causes T? And if you run this genetic programming algorithm, the first thing it finds is T equals P. So the more phosphorus in the water at that point in time, the more the toxic algal bloom. But as I mentioned, the situation is much more complicated than that. So it usually goes beyond that to N divided by P. For some reason, the ratio between nitrogen and phosphorus is a better prediction of a toxic algal bloom than just phosphorus alone. Turns out there is another equation beyond that and another one beyond that. It gets very complicated, but it starts to get better and better at predicting where and when there is likely to be a toxic algal bloom. Okay. There is, if you want to try this yourself, there's an application you can download off the web. So there's an application we developed at Cornell when I was a postdoc there. One of the students at the time spun this off as a startup company. You can go play around with this now, Eureka. You can download it, and when you download it and run it, and it starts up, it looks very much like a spreadsheet. You can drop some data into that spreadsheet, and then you can click Evolve. And when you click Evolve, it'll start giving you back equations that try to describe your data. They try and predict values in one column, in our case T, as a function of the variables in the other columns. You can put data from the lake in there, you can put financial data in there, you can put pretty much anything you want and see what kinds of predictions and what kind of equations you get back. Okay. Let's have a look at another genetic programming application here. So as I mentioned, genetic programming, the genotype is trees, and the phenotype in this case is the output of those trees. So actually, let me go back to our data set here for a moment. The genotype is the trees. When we take our tree and we plug in the values from a given row, we plug that into the tree, the value, the equation is computed, and it gives us back our y prime, or our prediction about how much algae was in the lake at that point in time. If we plug in the next row to the same tree, it gives us a different y prime. We have the same tree, we now plug in these values, it gives us back a different value. So if you think about taking a tree and plugging in this, then this, then this, then this, it gives us back a vector of numbers. And we then take that vector of numbers and compare it against our actual observations. And we're trying to minimize the distance between those two vectors. So that vector of values that the tree gives back, that's the phenotype of the tree. Make sense? Okay, so let's now look at a different application. We're going to have the same genotype. We're going to have a bunch of trees. And I'm going to show you a video. And from the video, I want you to try and think about what is the phenotype here? What is the thing that the tree produces? And what is the fitness function? Okay. So what you're seeing in the right-hand side of this video now is the best tree in the population at that given generation. So the right-hand side is a visual representation of the tree, of the genotype. What do you think those trees are encoding?
Polygons.
They're encoding polygons. So any given subtree in the tree here represents a particular polygon. If we dive down into one subtree that defines one polygon, what do you think you find in that tree?
Like coordinate information, like single color.
Right, so we want to know what are the actual positions of the vertices of that polygon and what is its color. So in this particular formulation of genetic programming, any given tree can encode an arbitrary number of polygons. For each one of those polygons, it can encode the geometry of the polygon, the vertices, and the color. Any computer graphics students here? There's one additional piece of information that each polygon has. Transparency, right? So if we just lie a whole bunch of opaque polygons on top of one another, much harder to approximate the Mona Lisa. But if the genetic programming tree can also play around with transparency, it can do a little bit of a better job. So the genotype is still a tree. The phenotype is a bunch of polygons. What is the fitness?
How close the pixels match the line on the left.
Exactly. So we take the phenotype produced by the tree. For each polygon, we take the red, green, and blue value of that pixel and measure how close it is to the red, green, and blue components of that pixel in the Mona Lisa. Minimize that error in the same way that we minimized error of equations in symbolic regression. Okay. Not a perfect likeness of the Mona Lisa, but given more polygons and enough time, you can actually run this to the point where it gets hard to be able to tell the original from the polygon approximation. Aside from a nice visual representation of genetic programming, could this have practical value?
Just face recognition?
Face recognition, how so?
Well, you had a picture of someone in a passport or something, and you wanted to match the computer or something you took with a camera.
Could be, all right. So we could maybe take the picture from a passport and produce this polygon approximation and compare it to polygon approximations in a database. Maybe we could do something like that. You could also use this for compression, right? Think about how many numbers it takes to describe the actual Mona Lisa. And again, if we wanted a really good approximation, we'd need a lot of polygons. But it turns out that the total number of numbers you need over here to describe a pretty good approximation of the Mona Lisa is orders of magnitude less than the numbers you need over here to describe the original. Maybe not the most efficient compression method, but kind of an interesting application of genetic programming. Okay, I think that that concludes our discussion of evolutionary algorithms. Any questions before we move on to physical simulation? Okay. So on to lecture 6, physical simulation. What I'm going to do is I'm going to walk you through the basics that you're going to need for this class. We could, again, have a whole course on physical simulation. It gets pretty complicated pretty quickly. We're just going to touch on the basics. Let's start by distinguishing what a physics engine is and what it is not. Typical 3D computer graphics programs, if you've ever played around with them, those that lack physics have all the same algorithm, which is for every object you need in the scene, you're going to define the geometric properties of those objects, right? So their position, the orientation, the shape of each object. Those objects are then placed into the scene. You render that screen. You then define the new position and orientation and shape of each object. At the next time step, render, repeat, and repeat, and repeat, and you'll get an animation of, for example, an object accelerating downward and hitting the ground and coming to rest on the ground. If you wanted to use computer graphics software to create an animation of a physical process, like a ball dropping and coming to rest on the ground, a pretty onerous task. Right? Physics engines, which sort of came into their own around 2000, said, let's try and build some physics in to simplify the creation of computer graphics. And in physical simulation, and there's a lot of physics engines that are out there now, they all share this basic algorithm at their hearts, which is a 3-step process. Rather than defining just the geometric properties of your object, like position, orientation, and shape, you're also going to define physical properties of those objects, such as the mass of the object, and maybe its friction properties. So are we dealing with a ball that's a steel ball bearing, or is it wrapped in sandpaper? How rough or how smooth is it, which dictates how it's going to interact with other objects. So define the geometric and physical properties of the objects. You may also want to define how the objects are attached together. So you saw that in the ragdoll physics example that I showed you. Once you've defined the geometry and physical properties of each object, how they're attached together, press go on your physics engine, and the physics engine does all the heavy lifting for you. It figures out what is the new position and orientation and velocity and acceleration of all the objects. You don't need to do it manually, which is what you had to do in pre-physics engine days. Okay, how does the physics engine do this? Well, it uses a formula that you've probably seen before. So again, going back to high school physics in this case, force equals mass times acceleration. If we reorganize this equation into acceleration equals force divided by mass, you've given the physics engine the masses of all the objects. We know which ones are attached together, so the physics engine can compute all of the forces that are acting on all the objects in your simulation. So in my very simple cartoon example here, let's say we start by defining a sphere that is hanging 3 meters above the ground, and we turn on our physics engine. What force is acting on that object? Gravity, right? So we have one force that's pulling downward at 9.8 meters squared, right? Okay. At the moment, assuming that there's no aerodynamics in here, let's imagine our sphere is in a vacuum, that's the only force that's acting on our object. We know the current position of that object, we know its mass, we know the force that's acting on it, so we know the acceleration that that object is going to experience at the next time step. So the next loop through the physics engine, it's computed this acceleration, it takes the acceleration and the current position of the object and figures out what the new position of the object is. Okay, it's got the new position, it's got the same force acting on it, so it knows the acceleration, so at the next time step, the position has changed even more than it changed at time step t plus 1. Right? So not surprisingly, the object appears to accelerate downwards toward the ground, and at time step 2, t plus n, it comes into contact with the ground. The physics engine computes this contact for you. We're going to talk about contact or collision detection, which is when they come together, and collision resolution, which is what does the physics engine do once two objects that have collided. We're going to talk about that in a minute or two. But intuitively, how do you think the physics engine deals with this situation, given what I've described about how it works so far? Obviously, the sphere should stop moving, right? It's come into contact with the ground. If we just use this equation, how is it going to resolve this issue? How is it going to know that the next time step the position does not change? High school physics again.
There's a new force acting upon it.
There's a new force acting on it, right? So gravity is still acting on the object, but the simulator realizes that there's a reaction force which is exactly opposite to the force of gravity. Those two forces cancel out, and from the physics engine's point of view, the net forces are zero. We plug zero into this. The acceleration of the object is now zero, and at the next time step, the object doesn't move, and the position of the object will stay there indefinitely until something in the physics engine changes. Okay. Again, as you start to learn about the Bullock physics engine, it's going to get complicated, but just remember that at its heart, this is all it's doing. Computing all the forces that are acting on all the objects, computing the new accelerations, and using that to compute the new positions. It paints or draws the scene, and around you go. And you get the ragdoll demo, and eventually, in your case, the robot demo. All right, that's the difference. Okay, let's start to now look at some of the parts of a physics engine. In this course, we used to use a different physics engine called Open Dynamics Engine, or ODE. So the little code snippets that you're going to see in the slides for this lecture are taken from ODE, but you're going to be implementing things in Bullet, which is a little easier to use than ODE. So you don't need to understand and memorize the code here. It's going to be slightly different for Bullet, but we're going to use this code to build up an intuition for what the physics engine is doing. When you run your physics engine executable, there's a bunch of preliminaries, so you need to literally set the scene. So you initialize the physics engine itself. You create a world, which is the virtual environment in which all the objects live. You create a space in which objects can and cannot interpenetrate. So we're going to come back to collision spaces in a moment, but a space contains all the things that should not pass through one another. In the example here, we have just two objects, which is the sphere and the ground, right? They shouldn't pass through one another. Pretty straightforward. Let's see. Contains all the objects that are in contact. So at any given time step, the physics engine is looking to see of all the objects that exist in the scene at the moment, which objects are in contact with one another and which aren't. So it can figure out how to apply these opposing forces. You can set the gravity to be whatever you want in this physics engine, and we'll talk a little bit about CFM a little bit later. The gravity part here is a reminder that you can make your physics engine more or less realistic given the physics here on Earth. Okay. Most important thing for us is adding bodies or objects to the scene. So as I've already mentioned, our body has certain physical properties. And in ODE and Bullet, they're going to separate for any given object. They're going to have two different data structures. And those two data structures point to the same object. One data structure contains all of the physical properties of that object. The other data structure contains all the geometric properties of that object. It's kind of a confusing way to do things. Why not have the same data structure for just one object? It makes things much easier for the physics engine. Just keep that in mind. Whenever you add a new object to the scene, you need to define a body which contains all the physical properties. We'll talk about the geometric properties in a moment. Okay,
So in this case, I'm creating a box, which obviously doesn't correspond to my picture over here. I've defined it as a 1 by 1 by 1 kilogram box. So I'm defining how the mass is distributed through the body, which gets complicated. So everything in this course, we're going to assume that mass is uniform inside an object. So when you create an object, there isn't heavier and lighter parts to the object. It all has uniform mass, which will make things easier. But you can do it differently if you want. We can adjust the mass a little bit once we've set it. We set the position of the object here, and in this case, I'm putting it 6 meters above the ground. So I've created a body, and I've defined the physical properties of it. As I mentioned, this is the ODE code that does that. There's similar code that does this in Bullet. Once I've defined the physical properties, I'm going to define the geometric properties, but I'll come back to that in a moment. There's a little aside I want to make here. When you set the position of your object, you can also set its orientation. So what is its angle about its axis? This is another thing that gets tricky pretty quickly. If you want to define how a three-dimensional object is oriented in space, we need to define how much it's rotated about one axis, a second axis, and a third axis, and about its own axis. So there's kind of 4 numbers that you need, which takes us into quaternions, which I would like to avoid in this class, and I imagine you probably also want to avoid them. Quaternions are a little difficult to work with, but just so you know what they are and how they're used here, let's imagine that I have a rectangular solid like you see here. I can use 3 numbers to define how the long axis of that object lies along a 3-dimensional vector. So x1, y1, and z1 here says take this rectangular solid, and I've told you about the physics of it. I've told you about the position of where it is. I want you to orientate it so that it lies along this 3-dimensional vector. And then the 4th number, theta here, represents how much that object should be rotated about its long axis. Okay. If you want to do that, you need to use quaternions, or things that are even more complicated. So for our purposes, we're going to be working mostly with cylinders, which are much easier, because then we only need 3 numbers, which define the long axis along which the cylinder lies, or the long axis, what vector does the long axis lie along, and because it's a cylinder, it's symmetric about its long axis, we don't need quaternions. So again, this is from ODE, but there's similar code that will allow you to define the orientation of an object in 3-dimensional space. Sound good? Yes?
How do you define where along the axis the body starts?
Good question. Okay, so let's go back to our 3-dimensional body here. Remember that we've already defined its position. So we're defining where the center of this object sits in the virtual world. So in our cartoon example here, our object sits at x equals 0, z equals 0, and y equals 6. So we're indicating where it exists in the world to begin with, and then by setting the orientation, we're basically rotating that object around its position. But the center of the object remains at 0, 6, 0 in this case. All right. So we're defining its initial state, but remember, once we turn on the physics engine, the position of this object and its orientation are going to start to change based on the forces that are acting on it. We only need to define the starting position and the starting orientation of our object. Okay. Okay, so we've defined the mass, the position, the orientation of our body. Now we take our body and we add this second data structure, which is called a geom or geometry, which you can think of as a skin that you're going to wrap around the object. Okay, so in this case, I'm creating a geom called box, a 1 by 1 by 1 box, a 1 meter by 1 meter by 1 meter box. I'm taking that skin and I'm applying it to the body that I just defined before, right? This 1 by 1 by 1 box in the code up here. All right, so now that I've done that, we want to try and use these to figure out collisions. But before I talk about collisions, just one more word about why we have these separate data structures. The reason why is that often you want to define a relatively complicated geometric object, and the physical properties of it might be pretty complicated because you've got mass in different places. So often you might create a geom, which is a more complicated skin that's wrapped around a physical object that's a little bit simpler. You're probably not going to need to do that in this class, but that's kind of the reason why these things are separate. Okay, so now, as I mentioned, once we have these geoms, the physics engine is going to use these geoms or these skins to figure out when things are colliding. So compute the distance between each geom pair. So look at two objects, see if they're close enough, look at the skins or the three-dimensional geometries of them, see whether they're in contact with one another or if the distance is less than or equal to 0. Not a good mathematical way to formulate this, but basically this describes interpenetration. So this can happen because obviously we're dealing with a physics engine here which is running on a computer. If I go back to the beginning, we are updating the physics in our environment in discrete steps. So our objects are actually moving in discrete jumps. And as long as those discrete jumps are small enough and we have a fast enough frame rate and you have a fast enough computer, you get pretty smooth motion. But if you do have objects that are accelerating relatively quickly, the jumps can be relatively large, and you might have two objects that are separate at time t, but at time t plus 1, they are now interpenetrating. And assuming you don't want them to interpenetrate, the physics engine will apply opposing forces to quickly move them apart at the next time step. Okay. I mentioned collision spaces. This is something you're also going to have to define. And the reason why we need collision spaces is because the thing that slows down a physics engine is not the number of objects in the scene. It's the number of possible collisions. All right? So let's take this space down here. Let's say we have one collision space. I've created 9 objects. Each of those objects has its own body and its own geom. And at every time step, we want to see whether every pair of objects in this case, or the physics engine needs to compute whether every pair is, any pair is colliding or not. How many comparisons do we need to do?
As many for each object, as many you have to have one equation for every other object, no matter how far away.
Exactly, right? So we need to see whether this one is in contact with this one or any of the other 8. Then for this one, we need to compare it to how many others?
Is that why we want to use simple shapes like spheres? Because the collision equation would just be whether their radiuses are
Exactly. So the easiest objects to compute to see whether they're in contact with one another are spheres. So there's the issue about how complicated is it to actually determine whether two objects are in contact with one another. And there's the issue of how many of those calculations you need to do. So this is the thing that slows down our physics engine, so we want to try and speed this up as best we can. So one thing you can do, and you probably won't get to this point, but if you do in your final project, remember this, which is you can put different objects into different collision spaces. Now, why would we want to do that? Well, let's assume that these things kind of tend to be together, and they tend to bump into one another more often than something here bumps into this, or vice versa. So now we can just look at the possible collisions in this space and the possible collisions in this space, and then there's one more thing we need to do. One more comparison we need to do. What is it?
Spaces getting close to each other.
The spaces themselves getting close to one another. If these two spaces are separate, we don't need to ask then whether this one collides with this one and whether this one collides with this one, and so on. Yes?
Do we ever fix collision spaces to like positions in the world? You know, like everything in these square meters
Right.
Are the collision space, and everything in these ones.
Not in Bullet. So in Bullet, you basically assign objects to a collision space, and that space follows that collection of objects as they move around in the scene.
Okay. How expensive is it to recalculate what's in which space?
They're assigned to each space. So when you define a geom, you assign it to a particular space. So you're indicating which objects belong to that space. So in this case, I've said these 4 objects belong to space 1, those 5 to space 2, and that's it. Okay. So in the interest of time, let's move ahead here. So in the simple case here, we need to compare this one to this one, 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 and I'm missing one, right? This one to this one. 6 possible comparisons. And so for each one of those comparisons, I need to ask whether those pairs are in contact with one another. Same thing for space 2. Now I have 10 comparisons. If I do the same thing down here, 6 plus 5 plus 4 plus so on will get us to 36.
I thought they,
Sorry, 9 plus 8 plus.
I thought programmers sometimes use bit mask or something so it's 1, 2, 4, and 8. So you get the sum, and then it can only return 2 numbers, say. So if you have 5, if it gets back 5, you know 1 and 4 are touching?
Yes.
Something like that?
There is a whole branch of computer graphics and computer physics that looks at exactly this issue about how to deal with this problem. The more objects that we have in the scene, the number of possible collisions goes up exponentially. And as you know in computer science, that's a big problem. So spaces is the simplest defense against this exponential increase. There's increasingly sophisticated defensive methods against it. Okay. You probably won't have this issue, but you might, depending on what you do for your final project. Okay. All right, so we've talked about objects, right? We've defined their physical properties, their geometric properties. We understand a little bit about how the physics engine deals with objects that come into contact with one another. What happens if we say they're objects which by definition are in contact with one another? We want to connect objects together. Well, we're going to do that with joints. For everything you're going to be doing in this course up to the final project, you're going to be creating rotational joints, which are not unlike your elbow joints and your knee joints, right? My elbow connects my upper arm to my lower arm, and it restricts the relative motion of those 2 parts of my body, right? Thank goodness for my elbow. I don't want my lower arm to physically separate from my upper arm. But I do want these 2 parts of my body to rotate relative to one another. So if we think about having 2 3-dimensional objects in our physics engine, and they're moving based on the forces that are acting on them, their positions are changing, and so are their orientations. When we connect 2 objects together with a joint, we're removing some of the relative degrees of freedom, meaning we're restricting how these objects can move relative to one another. So these objects can now change their orientation like this. And if you think about the centers of these 2 objects, the centers of these 2 objects, or the relative positions of these 2 objects, are also changing. But the positions are not changing relative to one another like this. So when you create a joint, you attach 2 objects together, like you see here. And the moment that you do that, it's going to restrict the new kinds of accelerations that the physics engine computes for that joint. A way to think about this is you're adding new forces that are acting on those bodies. So if I'm simulating my own body in a physics engine, and there are forces that are acting on my arm that is trying to pull my lower arm away from my upper arm, the physics engine knows there's a joint connecting those 2 pieces together and will apply another force pulling in the opposite direction that's strong enough that will make sure that the new position in the next time step ensures that my lower arm is still attached to my upper arm. That's the intuition behind joints. Okay, so not surprisingly, we start by defining this data structure, a hinge joint, which I just described. Which 2 bodies does it attach together? Where is the fulcrum? This is a place that, this is a part of physics engine where things often go awry. If you don't define the fulcrum to be exactly where the two objects come into contact with each other at the first time step, you get weird behavior. So I could attach my lower arm to my upper arm, but if I define the fulcrum up here, they may move in strange ways where they actually separate. So when you're building your robot and you start to attach the parts of the robot together with hinges and you see strange non-physical looking behavior, you've probably put the hinge or the anchor at the wrong place. Okay. Next place where things are often go awry is defining the hinge axis, or I think in Bullet it's known as the joint normal, same thing. If we're creating a hinge joint, which plane, which two-dimensional plane, should the two objects that are connected rotate through? Okay, let's stop for a moment and let's make sure we're clear on our axes. So we're dealing with three-dimensional physics engines here. X-axis is going to be left and right in the screen when you simulate your system. The Z-axis is into the screen and towards you, and Y is always the vertical axis. Okay, X, Z, and Y. Let's imagine that we have one object that's attached here, one object that's lying here, another object that's lying here, and we attach the fulcrum at 0, 0, 0, so that's good. We now define the axis, or the joint normal, as a three-dimensional vector. And let's imagine that in this case we define this, this joint normal as x equals 0, y equals 1, z equals 0, so vertical axis. By doing that, we've defined the plane through which these two objects are going to rotate, which is the plane that is perpendicular to the vector, right? Back to high school math again. If we define a three-dimensional vector, we have also defined one and only one two-dimensional plane that is perpendicular to that vector. Okay. If I instead attached these objects together and I wanted them to rotate through this vertical plane, what would my joint normal be? So if I want these two objects to rotate like this through the horizontal plane, I define this vertical vector. If I want them to rotate like this, first of all, what plane am I rotating through? The xy plane, right? The x and y coordinates of this object are changing, but its z coordinate is not changing. So what's the joint normal that will define that plane? I want the two objects to rotate through the xy plane. The z-axis, right? So when I call this function, I would call it with 0, 0, 1, which is this vector, right? The z vector that's pointing into the screen. It doesn't actually matter if you can also do 0, 0, minus 1. The orientation of the vector doesn't matter as long as it's along the z-axis, and that will define this joint. Okay. Remember that when we're setting the scene here, this is basically all preliminaries. We're creating our initial scene. Once the scene starts up, these two objects might start moving through the space in very complex ways, depending on what forces are acting on them. And the joint normal is also moving so that these things continue to rotate through the xz plane relative to themselves. Thankfully, you don't have to worry about this, right? This is why we use physics engines. It's figuring out what the new joint normal is, what the new plane is that the objects are rotating through, and so on. Okay, so far so good? Okay, I think let's stop there before going on to the other aspects of the physics engine. Let's see, it's Tuesday, so you've got assignment 4. Get started on that early so you can figure out installation hassles. You have a quiz that's due tonight. Good luck. See you Thursday morning.